Hello folks, hope you're doing well for your senior ditch day. Anyways, I'm recording this because this would have been part of the lesson that we would have gone through. But I thought maybe if you have it recorded, then that you'd have it along with your notes. So this is going over section 8.5. We talked about, the last thing we talked about ages ago was about dealing with piecewise continuous functions and using the step function in order to do that. So more generally now we're going to solve for differential equations that have constant coefficients on one side, and then the forcing function will be a piecewise function, which will need to use the unit step function. All right, here's a theorem that says a, b, and c are constants, and then you have a function f that's a piecewise function with a finite number of discontinuities, and then k naught and k1 are arbitrary real numbers. Then you can let your k1 and k naught and k1 be your initial values, and then you will be essentially guaranteed y and y1 to be continuous solution. Y double prime will be defined on open interval that doesn't contain any of those endpoints, so it might be discontinuous by the time you get to y double prime. And then y double prime, even though it's discontinuous, it'll still have a limit from the left and from the right. In other words, it doesn't all just jump up to infinity or anything like that. So those are the key things that this theorem guarantees for us. We'll have a continuous solution is basically the bottom line. Now, if you were to solve for constant coefficient equations with piecewise continuous forcing functions, here would have been your algorithm. You have the left-hand side is just a general equation that we've seen before, and your right-hand side would be some piecewise function. And so what you would do is you would solve for the function from 0 to t sub 1 using the initial conditions. And then from there, you get a solution for that. You're going to get a new set. You're going to get a y sub 0 solution. And then you're going to get a new set of initial conditions, and then you would have to resolve with a second function, and with the new initial conditions, instead of k naught k1, you're going to use the c naught c1, which came from your first solution. And then your final solution will look like this, a combination of the y naught and y1 functions. Now that's how we would have done it if we didn't have the unit step function. But since we have the unit step function, and we also have the ways to transform that into the Laplace world and back, then we're going to use that. So we're going to do some problems, but before we do those problems, we'll just remind ourselves of some of the things that we've discussed already about piecewise functions. So piecewise function can be written as those piecewise pieces of the function with some unit step function being multiplied. Okay, so we did this. We had some exercises on transforming a piecewise function into a unit step function, and then we should also be able to go backwards if we want to. And then the other big theorem was being able to use this idea of the shifting theorem. And this shifting theorem tells us that if we have a piecewise function that jumps, so u is your piecewise function, and if your function g has the same shift as the unit step function, then you can transform that. You can transform this into the Laplace transform of the original g function with an exponential function in the Laplace world. Okay, so in the Laplace world, we will have an exponential function. So basically, the shift here tells us that if we have a shift in the t world, in the real world, then we would have an exponential function in the Laplace world. And if you remember the first shifting theorem, if we have a shift in the Laplace world, then we have an exponential function in the t world. Okay. All right. So basically, this is the transformation that we're going to want. All right. So let's practice doing some of this. We have an equation that's y double prime plus y equals to this piecewise function. That's a 3 as long as t goes between 0 and 4, and 2t minus 5 when t is bigger than 4. And we do have this y of 0 is equal to 1, y prime of 0 is equal to 0. So these are your initial conditions. All right, before we transform this, let us first rewrite our piecewise function. So let's say this, we'll call this f here, f of t. And if you remember what that was, it's going to be the first function plus the shift times the difference between the second function and the first. So it's the first function is 3 plus the shift. So the shift is t minus 4 times the difference between the second function, 2t minus 5 minus 3. All right, so this is going to be 3 plus the shift. I usually like writing the shift on the other side, so let me write this first. So it's 2t minus 5 minus 3 is 8 minus 8, so 2t minus 8. And then you have your shift u t minus 4. Okay. All right, so we will do the Laplace transform to get to the Laplace world. And in the Laplace world, we will have this left-hand side. So remember, y double prime starts off with an s squared capital Y minus y, it's going to be s times y of 0 minus y prime of 0. So this whole thing is the y double prime. And then we just have a plus y, so that's just the capital Y here. And then we have the right-hand side, which is going to be the transformation of this. So before we get there, I guess we should step back. And because the transformation needs to have the same shift as the step function, the g has to have the same shift as the step function. In other words, I need a t minus 4 in there somewhere. So I think luckily if we just factor out a 2, and we'll get a t minus 4 kind of already set up, times u of t minus 4. All right, so that's what this becomes. This is going to be important for us because what we're going to need is a transformation of 2t. So we're assuming that g is equal to 2t. And if this is the f in the, I guess I'm calling it f, let's call it h. If this is some function h of t, then the capital H of s in the Laplace world is going to be the transform of t, which is s squared. And then we have 1 over s squared, but then we're multiplying it by 2, so that's 2 over s squared. All right, so this whole thing will transform to, I guess we should have just called it g. Let's call this g, and let's call this capital G to refer to this g and this capital G. So this is your g, and then g of t minus 4 is 2 times t minus 4, and then you have the u of t there. So this is going to be capital G of s, our transformation, and we need to multiply that by e to the negative as, where a is equal to 4. All right, so let's come back here. This is the transform of 3, that's 3 over s. The transform of 1 is 1 over s, and you have a constant 3. And now here comes this business over here. This is going to be g of s, that's 2 over s squared, times the exponential function e to the negative, and then the shift is at 4s. Okay, that is your, now we're in the Laplace world. That's your transformation. We are now in the Laplace world. Let's solve for capital Y. We're going to use y of 0 is equal to 1, and y prime of 0 is equal to 0. So this is going to be s squared y minus s minus 0 plus y is equal to 3 over s plus 2 over s squared e to the negative 4s. All right, let's bring this over to the other side, and let's factor out a y. So this is s squared plus 1, capital Y. And then let's bring this over to the other side, so that just becomes a positive s plus 3 over s plus 2 over s squared e to the negative 4s. Now let's solve for y. Y is equal to, we have to divide each one by s squared plus 1. So this is s over s squared plus 1 plus 3 over s times s squared plus 1 plus 2 over s squared times s squared plus 1 times e to the negative 4s. All right. We're almost ready to transform this back. This can be transformed. S over s squared plus 1 is simplified. This will need some partial fraction work. And let's just say I'm going to punch that in Wolfram. And in Wolfram, I get a plus 3 over s minus 3s over s squared plus 1. I suppose I could have combined these, because it looks like I have two s over s squared plus 1 things that I could have just had one of. Maybe I'll rewrite that in a bit, because I also have to do the partial fraction decomposition for that one. And that one is 2 over s squared minus 2 over s squared plus 1. And these both have the e to the negative 4s attached to them. All right, I'm going to do just one more step here. 3 over s minus 2s over s squared plus 1. And then I have 2 over s squared minus 2 over s squared plus 1 e to the negative 4s. That is y. Okay, now let's bring it back. So this is the Laplace inverse, the inverse Laplace transform of this, which will bring us back to the real world where we have y of t. All right, so what's y of t equal to? 3, and then 1 over s is just going to be 1, so I'm not going to bother with that. I'll say maybe off to the side here, the inverse Laplace of 1 over s is just going to be 1. The inverse Laplace of s over s squared plus 1, if you remember, is the cosine function, cosine t. This is s squared. The inverse Laplace of 1 over s squared is just t. But when we do this, we're going to have a shift. So let's keep that in mind. Inverse Laplace of 1 over s squared plus 1. Remember that this 1 here has to match with this one, so that 2 will just get taken out. Not match, but this should be 1 squared, and this is going to be 1. This is sine of t. All right, so now we have all these Laplace transforms. We have a minus 2 cosine t. Now here comes a shift. So I'm going to put a parentheses, and when we bring this back, according to the theorem, when we bring this back, we're going to need to bring that back with a shift. All right. So this is t, so this is 2, and then this is t, so we need to do that shift. T minus 4. times u to the t minus 2 u of t minus 4. So that's the first one, and then the next one is going to be a 2, and then it's sine t, but remember the shift t minus 4, and then that's it. We close that off. All right, that is our setup. Let me see, I think I have the graph of this here. The graph in blue is the original forcing function. It goes up and then goes up. And then this, I also included the graph of the solution to the homogeneous differential equation using the homogeneous differential equation. That is just this part here when this thing is set equal to 0. And I assumed that this thing was set equal to 0, and I used the initial conditions, and then I got this graph in purple. Now the actual graph that we want is this graph. This is 3 minus cosine, and then you have the other part of the function here with a shift, and then it brings us to this. So it kind of follows along that blue line, and it has that wavy thing that it had from the homogeneous equation. So here is your solution. All right. Okay. Before we go on to the next problem or two, we're gonna just pause and let you all soak it in, and then hopefully it'll help. Actually, here is the next question. If you want to start looking at it before you go to the next video, you should take a look at it, give it a shot, and then go back to the video, the next one. All right. Okay, I hope you took a pause to try out this problem. We're going to go for it. All right, just like before, we will rewrite your piecewise function f of t to be in terms of the unit step function. So it's going to be the first function, e to the 2t, plus the step function with the shift at whatever that shift is, times the second function minus the first function. Okay, so this is what we have. Now we're going to need to transform this, and what we need out of the functions being multiplied with the step function is that we need to have the same shift. We need a t minus 2 in here. Now this is constant 1, that's not a big deal. But if you have a e to the 2t and you want to shift this, you want some sort of imaginary factor out of 2, so we need to kind of have a minus 4 there. Now clearly you can't just subtract 4 from the exponent, but if you add 4 at the same time, then maybe you're essentially adding 0, which makes it an okay move. What does that mean? That means you're going to get e to the 2t minus 4 plus 4, so e to the 4th. E to the 4th is just constant, but now you will have an e to the 2 parentheses t minus 2, which is that shift that's needed. And so now we are going to be able to rewrite this e to the 2t in terms of something that has a t minus 2. All right, let's just rewrite that, e to the 2t. I don't know why, but I usually like writing the step function last. So I have a constant 1, and then I will have an e to the 4. I'll write that first because that's constant, times e to the 2 parentheses t minus 2, which we already have it set up here, and then u t minus 2. All right, that sets us up to be able to make that transformation to the Laplace world, which is our next step. Transform to the Laplace world. So y prime again is s squared capital Y minus s times y of 0 minus y prime of 0. And then we have just the y is equal to, now let's do the transformation here. e to the 2t is 1 over s minus 2. And then now we have the transformation with the step function that is going to give us a transformation with the e to the negative 2s power, the exponential. All right, so the 1 transforms just into 1 over s. And then you have a constant e to the 4. Don't forget that e to the 4 is just constant. And we really just want e to the 2t transformed. And so the transformation of that is just, again, it's the same as this. So it's 1 over 2 or s minus 2. So that's what we will have here. 1 over s minus 2. All right? Okay, so just so we know where these things come from, that's from there. This is from here. And because of this shift, we have this exponential function. Those are all grouped together. Okay, let's put in some values that we can get from the real world. Y of 0 is equal to 3. This is going to be negative 1. So let's see. Let's write it here first. S squared y minus 3s minus negative 1 minus capital Y. I guess I could just say y because we're in the Laplace world. That's understood to be capital Y. This is by itself, s minus 2. And then this is together, 1 over s. I'm not quite sure if I want to mess around with this e to the 4th and put this as one fraction, so I'll keep it separate. And I'll just abuse Wolfram to give me all the answers for all the partial fractions that I'll eventually need. All right, so we have everything there. Let us bring these to the other side, factor out a y. So we have an s squared plus 1y. And then we'll have a 3s minus 1. So the signs change when it goes to the other side. And then I also have this 1 over s minus 2 plus the rest of this. We haven't done anything yet in terms of changing these expressions. And so I'll divide by, oops, let me get rid of this. Okay, now let's divide by s squared minus 1. So this is going to be, maybe we should have combined this. Let's put this together. This is going to be a 3s minus 1 times s minus 2 to get a common denominator of s minus 2. And I'm putting it here because I'm going to divide by that also. So what is this numerator going to be? There's a plus 1 over here at the end. So this one foils out to 3s squared minus s minus 6. So that's minus 7s. And then plus 2 plus 1. So that's a plus 3. So that's going to be 3s squared minus 7s plus 3 in the numerator. And we were on our way to dividing by s squared minus 1. Here I will get 1 over s squared minus 1 minus e to the 4th. And this is going to be s minus 2 s squared minus 1. And then the e to the negative 2s, which tells us that there's a shift in the real world. All right, now let's start breaking those apart. With the use of Wolfram alpha, I will be able to break this apart, and I think I have the answer. It's 1/2 times 1 over s minus 1 plus 13 over 6 times 1 over s plus 1 plus 1/3 1 over s minus 2. So that's the first part right here. Now all this other stuff in in the parentheses is going to get really long, so let's put brackets there. This first one breaks up to 1 over s plus 1/2 1 over s minus 1 plus 1/2 1 over s plus 1. So that's the first one. And then I have e to the fourth, which is constant in the transformation. I'll just leave it out as constant. And then this thing here will transform into 1/2 1 over s minus 1 plus 1/6 1 over s plus 1 plus 1/3 1 over s minus 2. So all this is multiplied by e to the fourth, and this whole thing, starting from here in the beginning, will get multiplied by e to the negative 2s. And we only want that to remind ourselves that all these things in the bracket, square bracket, will get multiplied by by u, the unit step function, u of t minus 2. All right, let's Laplace back, inverse Laplace, and now we're ready to write our actual solution. If we remember some of these transformations. So the transformation from this inverse transformation back is going to be e to the positive t, 1 times t, so it's 1/2 e to the t plus 13 over 6 e to the negative t plus 1/3 e to the positive 2t. So that's the stuff that does not shift. That's not part of the shift. Now the part that's part of the shift will multiply by u at the end here. And what are those? So this is going to just be a 1 plus 1/2. Now remember, when we shift back, this is going to be e to the t. Let's write that down. This transforms back to e to the t, but this includes a shift. So this is going to be e to the, instead of just a t, it's going to be a t minus 2, because that's the shift that we have. And this next one is going to be 1/2. This is going to be e to the negative t. So it's going to be negative t minus 2. All right. Now let's get busier here. This is a 1/2 e to the, again, t. So that's t minus 2 plus 1/6 e to the negative t minus 2, and then a 1/3 e to the 2t, but instead of t, it's going to be t minus 2. All right, so close that up, and remember this goes into the shift t minus 2, u of t minus 2. All right, that is your solution. Let's see if I have the graph for this. All right, here goes the graph. It's not very interesting because you got a lot of exponential functions, and I think it might be better if we expand this and shrink the y, and maybe this is the way to look at it. This is the solution to the complementary equation. The original blue is the piecewise function, so it's an exponential function. It jumps up until you get to 2, and then it remains constant at 1. And so this is the homogeneous, the complementary solution, and the actual solution that we're looking at looks like this. It looks like it breaks off, so it's supposed to be continuous, so something must have happened. Let's check that again. All right, looks like we got a couple of errors here, and looking back at Wolfram's work, this should have been, when it did the partial fraction decomposition here, this should have been a negative. Maybe I'll make a note here. This is Wolfram. And then there's a negative that should have been here, and more importantly, there's a negative that goes over here. All right, so if we follow that negative here, our final solution will have a -1 here, and this exponential should be negative there. And so fixing up my Desmos, putting those negative signs where they weren't before, here is now my solution. The solution is in red. Solution needed to be continuous even at that break. So the original f of t piecewise function breaks off here, and but the solution needs to be continuous. And also smooth enough because the derivative also has to be continuous. Okay, all right, that's our second one. Now peek at the third one and then give it a shot before, pause the video, take a look at this, pause the video, give it a shot, and then let's see how you do. And then I'll provide the solutions. Okay, we're back. I hope you give it a shot. But I will give this a shot and we'll see how it goes. All right. In the real world, we are looking at this function here, f of t, and writing it as a step function. So this will be cosine t plus the sine t minus cosine t, u of t minus 3 pi over 2. Now we have a bit of a problem here because we want functions that look like t minus 3 pi over 2 and sine of t minus 3 pi over 2. But we have cosine and sine here, sine and cosine. So what we need to do is we need to use some sort of formulas to see if we can write sine and cosine to be one of these two functions that maybe would have a negative in front or something, linear combination of these two things. So best thing to do, I mean, if you know the formulas, that's great. If you don't, I would just graph this. So let's go to Desmos real quick. And let's graph cosine of x minus 3 pi over 2. And I'm looking at this and they say, hey, this looks awfully close to the sine function, except it's negative. So maybe if I throw a negative in front of this, and that looks exactly the same as a sine function. So it looks like the sine of t, which is here, and I'll need to replace the sine of t. I can replace that with a negative cosine. So I'll say negative of this, maybe I'll do this in a different color as we're exploring. The negative of this is equal to the sine of t, and I can make that replacement there, and then I would have a function that has a t minus 3 pi over 2. Remember, we want to match the 3 pi over 2 in the shift. All right. I'm hoping that the sine will look a lot like the cosine. So let's put these away and let's draw the sine of x minus 3 pi over 2. And it does look like a cosine, and it looks exactly like the cosine. If I compare that with a cosine function, it's exactly the same, right? So this is exactly the cosine function. So now I can make those replacements, and then I will have functions with a shift already attached to them, which would be great because that's what we want. So the cosine t here is not part of that shift. That's the first function. It's not part of the step function. But now I have sine t. Sine t is actually equal to negative cosine of t minus 3 pi over 2. And then I have a cosine t, which is actually equal to sine t minus 3 pi over 2. And now I have functions that match with the unit step function shift, t minus 3 pi over 2. All right, now I will be ready to do the Laplace transform into the Laplace world. All right, we have s squared capital Y minus s y of 0 minus y prime of 0. That's the first one. And then now we have 9y, and without any others, the other thing, because it's not part of the, there's no more derivatives. And now we come to the right-hand side, which is this piecewise function. Start off with a cosine. Cosine transforms into s over s squared plus k squared. K is just 1. Now, in parentheses, we will transform with the shift. So just the transformation of cosine t here, well, with a negative sign. And we saw that to be s over s squared plus 1. That's a cosine t. And then a negative sign here again, the transformation of sine is 1 over s squared plus 1. And those are my two trig functions inside. And in the shift in the real world gives us an exponential in the Laplace world. And the exponential function will be 3 pi over 2s. Okay, that's that. Good news, these are both equal to 0 because my initial conditions are equal to 0. And so I am well into the Laplace world solving for y. So I have s squared plus 9 times y equals s over s squared plus 1, and then this other stuff. I'm tempted to just put it together since they all have common denominators. So negative s minus 1 divided by s squared plus 1 e to the negative 3 pi over 2s. And so we'll get y by itself. And I have s over s squared plus 1, s squared plus 9, plus negative s minus 1 divided by s squared plus 1, s squared plus 9. And this gets multiplied by e to the negative 3 pi over 2s. All right, this looks like a job for Wolfram. So here it goes. S divided by the product of s squared. It should be s squared plus 1, s squared plus 9. And it looks like it's going to be a couple of cosines thinking and transforming back. So I'll rewrite that. Here, y is equal to 1/8 s over s squared plus 1 minus 1/8 s over s squared plus 9. Interesting that there's no constants up on top. And then now this thing, let's see how this transforms to. And if you have the previous command here, I just put negative 1 minus s, and with the same denominator should give us our result. now we have a combination of s's and constants. So this is going to be minus s minus 1 divided by this an 8 here, s squared plus 1, and then plus s plus 1 over another 8 here, and then s squared plus 9. And we have the exponential, and then now we're kind of ready to transform back. Just a little bit of a warning here. This is a combination of x's or sines and cosines, just for practice. This is 1/8, and then this is going to be there's a negative in both of them, so I'll just take out a negative 1/8, and then this is going to be s over s squared plus 1 plus 1 over s squared plus 1. Trickier here, you do get that 1/8 again, and this is s over s squared plus 9, so that's not an issue. But the next one is 1 over s squared plus 9. Now, according to the Laplace transforms, Laplace transform of sine kt is equal to k over s squared plus k squared. And so we're going to need a 3 up here, which means we're going to need to multiply this by 1/3. So keep that in mind when we're doing the transformation back. Transformation back, ready to go. Inverse Laplace, back to the real world, y of t is equal to. Our first function here is a cosine function because there's an s, so that's 1/8 cosine t minus 1/8 another cosine function, but now there's a 3t. And for cosines, we don't have to worry about the constant because they just require you to have an s in a numerator. But for the sines, they will require you to have that same constant. Okay, now we are into the parts that has the step function. So we'll start off here, negative 1/8, and that's a cosine t minus 1/8, and then that's a sine t, and then now plus 1/8, and then this is going to be a cosine 3t. Now this is the tricky part. We have a 1/8, but then we also need to extract this 1/3 out. That gives a 3 in the denominator. And then that will leave you with a 3 over s squared plus 9, which is going to be a sine 3t in the inverse transformation back. Now all this, remember, was part of a shift. So the shift is going to be the step function u of t minus 3 pi over 2. All right, and that is your result. Okay, so I hope that helps. This is how we solve for these equations using the unit step function. All right, we got some more to do, so but this is the end of this video. This is section 8.5. Good luck.